Welcome to the second video of our Unit 3 review. I'm going to jump right in. We are on question 8, which says gasoline, C8H18, burns in the carburetor of a car engine according to this reaction. So here it is. We've got two C8H18 molecules plus 25 O2s, and it's producing 16 CO2s and 18 H2Os. Okay. 8A says, how many moles of oxygen react with 0.4 moles of gasoline? So again, when they give you a chemical equation and you're looking at two different substances, so X, we're asking for X moles, how many moles of oxygen, which is O2, react with 0.4, that's our given, 0.4 moles of gasoline, C8H18. Okay, so this setup is for one where we're using equivalent fractions. We want to put our given on the bottom and our required on the top, so we'll start with that. 0.4 moles C8H18, and on top X moles of O2. We'll set up an equivalent fraction, moles of O2, right? Whatever is on the top here will go on the top over here. Whatever's on the bottom will still be on the bottom. Same kind of fraction that we're setting up. And we'll take our moles from a relationship about moles that we know. So O2 looks like there are 25 moles of O2. So we'll say 25 up here. And gasoline looks like there are 2 moles of gasoline in that equation. So for every 2 moles of gasoline, we need 25 moles of O2. So for every 0.4 moles of gasoline, how much do we need? Right. So let's solve for our X. We'll say cross multiply, we'll say X times 2 gives us 2X, and 0.4 times 25, doesn't matter the order. There we have it. Okay, and we'll divide both sides by 2 to get that X all by its lonesome. So X equals, and we're going to put this in our calculator, we'll say 0.4 times 25 divided by 2 gives us, so yeah, of course, 5. And 5 moles of O2. In the question, we were given only one digit, so in our answer, we only have one digit. That's fine. So final answer. Let's look at 8B. According to the same reaction, what mass of carbon dioxide are required to find as X grams of CO2 are given? What mass of carbon dioxide is formed if 452.0 grams of gasoline react? 452.0 grams of gasoline. Okay, same kind of situation where we are comparing two different substances and we have a reaction, so we are going to have to set up an equivalent fractions. We'll put our X grams of CO2 are required on the top, and our 452.0 grams of C8H18 on the bottom. And we'll pull those units over, so GCO2, GC8H18. And how are we going to get these grams? Well, we are going to have to find the molar mass of each of these things. So let's start with CO2. Carbon, when we pull it from the periodic table, is 12.0, and there's one of them. Oxygen is 16.0, and there's 2 of them. So when we add that up, we get, well, 2 16s is 32, plus 10 is 42, plus 2 is 44, 44.0. So 44.0 grams of CO2 times the number of moles of CO2 that we need, which is 16. So put that 16 in there. Let's do the same thing for C8H18. We have 8 C's and we have 18 H's. So when we add all of that up, I'm getting 114.0. So we'll put 114.0 down here, and we'll multiply by the number of moles of gasoline that we have in our equation, so 2. Okay, so let's go ahead and do some of that, some of those calculations. So we have 16 times 44 gives us 704, and we have 2 times 114 gives us 228.0. Over here we still have our x and our 452.0. So let's solve for x. We'll do our nice cross multiplication. 228.0x equals 704.0 times 452.0. Okay, we will divide by 228.0 on both sides to get x all by itself. Cancel, leave our x, and let's put that in our calculator. 704 times 452 equals, divided by 228. Now I'm getting 1,395.64. We need 1, 2, 3, 4 digits, 0 counts because it is at the end of the number and after the decimal. So we've got 4 significant digits here. So my calculator is saying 1395.649 blah blah blah. We're going to keep 4 digits, 1, 2, 3, 4, and round to 1,396 grams of CO2. Oh, and there's your final answer. Okay, that's number 8. Let's move on to number 9. All right, number 9 says, compare the arrangement, movement, and attraction of particles in a solid, liquid, and gas. So let's do it this way. Solid, liquid, gas. Arrangement, movement, attraction. Okay. So arrangement for solids, liquids, and gases. So the arrangement in a solid, the particles are close together. and they're stuck in place. In a liquid, they are still fairly close together. Not as close as solids. And they can roll past each other. A little messy there, but they can roll past each other. In a gas, they are far apart from each other. And that's it. They're just really far apart from each other. That's all. They're not stuck. They're totally independent. Let's say that. And also, their movement is independent. So, movement, solids, they vibrate. That's it. Liquids, they vibrate, and they also rotate. And gases vibrate, rotate, and also translate, meaning they move in a straight line. Move in a straight line. Okay, attraction. Here, they are very attracted to each other. In a liquid, they are moderately attracted. In a gas, not at all attracted. Okay. And if you get a question like this where you're making several comparisons on your test, you can put it in a chart form if you like. That's totally up to you. So that's our question 9. Let's look at question 10. Question 10. A can of shaving cream has this warning: contents under pressure, do not place in hot water or near radiators or stoves. A says, use the kinetic molecular theory to explain the warning. Okay. When particles in the can of shaving cream are heated, they move faster, they hit the walls of the container harder and more often. Thus, the pressure inside increases and may lead to the container exploding. Alright, so that's why you want a warning on the shaving cream, because it might explode. So here's the thing about this answer is that when you're talking about kinetic molecular theory, you must talk about the movement of the molecules. So you can't just say increased temperature leads to increased pressure, because that's not explaining about the molecules. So the kinetic molecular theory really does push you to think about these relationships in terms of molecules. Okay, and it says, what gas law does this demonstrate? Sorry for the little pause there. Getting back to it, we're looking at 10b. 10b asks, what gas law does this demonstrate? So in our question, we were looking at temperature and pressure. So this is P1 over T1 equals P2 over T2, which is Gay-Lussac. All right. Number 11 asks us, in February, you paid $2 for a beautiful helium balloon for your child's birthday. You leave the balloon outside in your car, and when you return an hour later, it's much smaller. A, should you take it back? Use the kinetic molecular theory to explain what happened. Okay. So when you took the balloon into the cold, right, because it's February, you took it outside. When you took it into the cold, the molecules inside the balloon slowed down because the temperature dropped. They hit the sides of the balloon less often and with less force. Thus, the balloon decreased in volume. You do not need to return the balloon. It will inflate again when you bring it in a warm room, right? Okay. 11b asks, what gas law does this demonstrate? Here, we're looking at temperature and we're looking at volume. V1 over T1 equals V2 over T2. And this is Charles' law. Okay? Number 12 asks us to describe 3 ways that the particles of an ideal gas behave. When we're talking about an ideal gas, this is just asking about the kinetic molecular theory and to state 3 of the 5 tenets of the theory, 3 of the 5 ideas that we reviewed in lesson 8. So let me just give you all 5 of them. The question is only asking for 3, but just in case you came up with some combination of 3 that someone else didn't find, we'll give you all of them. So number 1, molecules are small and far apart. Number 2, they move independently. So pendently. This means there are no intermolecular forces. We also know that they have elastic collisions, meaning that they, when they collide, the total kinetic energy going into the collision is the same as the kinetic energy coming out. So they have elastic collisions. They don't slow down by banging into other molecules. Number 4, they move really fast. And number 5, the higher the temperature, the faster they move. All right, that's it for number 12. Flip her on over to number 13 on the other side of your printout. 13 asks us to use the kinetic molecular theory to explain why the pressure of a gas in a sealed syringe increases as the volume of the syringe decreases. As the volume decreases, the molecules inside hit the walls of it's a syringe in this case, more often. Let's say these collisions lead to increased pressure. Okay, let's look at number 14. Distinguish between good and bad ozone. Good ozone and bad ozone. Good ozone protects from UV radiation. Good ozone is high up in the atmosphere. We're talking like 25 kilometers up. Bad ozone is low ground level. It comes from emissions from cars and trucks. And bad ozone can lead to some pretty nasty things, respiratory problems, and lack of photosynthesis, and degrading of rubber and metals. Good ozone protects from illness caused by sun damage, damage like skin cancer. All right, that's it. Number 14. 15. What type of compound destroys the ozone layer? This is CFCs. 15A. B says What is the element in these compounds which does the damage? It's chlorine. 16. Name one greenhouse gas. This might be CO2. That's the one that we studied. There are other options, but that's the one that we looked at. What produces this gas? Burning of fossil fuel. Coal, oil, gas. How do greenhouse gases affect the environment? They trap in heat energy from the sun and give it a chance to be absorbed more often, leading to increases in the temperature of the atmosphere. All right, 16 down. 17 says, what two gases make up most of the air? Nitrogen is 80% of the air, while oxygen, I guess it's N2 and O2, oxygen makes up 19% of the air. The rest is CO2, H2O, a little bit of pollutants, makes about 1% depending on where you are in the world. Okay. 18. Give 3 medical uses of compressed oxygen gas. Okay, this is actually something that we did not get a chance to discuss in class, so this will be bonus for everybody who views this review. Give 3 medical uses of compressed oxygen gas. We can use it for a few things in medicine. We can use it to treat, so let's say treat respiratory illnesses. And we can essentially name any of them, and you probably will be correct in terms of using compressed oxygen gas. So when you can't breathe, you might have a little tube that puts oxygen kind of into your nose. So this might be pneumonia, lung cancer, emphysema, excuse the spelling, etc. Compressed oxygen gas is sometimes used for newborn babies. When their lungs are underdeveloped, they might need some compressed oxygen gas. Alright, we can leave it at that. Any of these would be fine, as well as newborn babies. It's also used in barometric chambers, and this might be to reduce inflammation. Sometimes it's used in sports medicine in that way. Okay. Same thing for number 19, bonus here. 3 uses of nitrogen gas. Nitrogen gas is used for when it's like liquid. Well, nitrogen gas can be liquefied to flash freeze products. These don't have to be medical uses, right? Just uses. Flash freeze products. It can be used to treat warts. If you've ever gone to get a wart frozen at the doctor's, that's what they use. And it also can be used to cover produce, like when your fruits or vegetables are in a truck, they cover it with nitrogen gas to reduce the chance of rotting. Rotting is a process that requires oxygen, so if there's only nitrogen around, rotting can't happen as easily. So they blanket these things in nitrogen gas. Totally harmless as most of our atmosphere, but it does block the oxygen. 20. What is absolute zero? This is the temperature at which molecules have no movement. It's 0 Kelvin or minus 273 degrees Celsius. All right, on to question 21. A syringe contains 50.0 milliliters of a gas at a pressure of 101 kilopascals. The end is sealed and the plunger is pushed to compress the gas to a volume of 12.5 milliliters. What is the new pressure, assuming constant temperature? Okay, so we'll start with P1 V1 over T1. We'll just start with the whole equation here, the combined gas law. And the question says, assuming constant temperature. So we can take out the T's and just worry about the P's and the V's. So down the side here, I'll say P1 V1 P2 V2. Okay, let's take some of these numbers and plug them in. The syringe contains 50 milliliters of a gas, so that's a volume, 50.0 milliliters, at a pressure of 101 kilopascals. The end is sealed and it's pushed, and then the volume is 12.5 milliliters, so that'll be V2. But we don't know what P2 is. The question says, what is the new pressure? So that makes sense that we should have no information about P2. It kind of confirms. So that's good. Let's set up our equation then. Without the T's, it looks like this. P1 V1 equals P2 V2. This is Boyle's law for those of you who are trying to remember which one's which. Here it is. So let's replace our variables with our numbers. So 101 times 50. P2 we don't know, and V2 is 12.5. Now we want P2 all by itself, so we will divide by 12.5 and divide by 12.5 to keep them equal. This cancels. We're left with P2. Let's type it into our calculator and find an answer. 101 times 50 divided by 12.5 gives us 404. And now we were measuring in kilopascals, so this will be in kilopascals, kPa. And also we have 1, 2, 3 digits, 1, 2, 3 digits, because that 0 is at the end of the number and after that decimal. And 1, 2, 3 digits, so we need 3 digits in our answer, so 404 is all set to go. That's it. Let's look at number 22. A storage tank is designed to hold a certain volume of butane gas at 150 kilopascals and 35 degrees Celsius. To prevent dangerous pressure buildup, the tank has a relief valve that opens at 250 kilopascals. At what Celsius temperature does the valve open? Okay, so we're seeing that we've got pressure and volume and temperature in there. Well, do we have a volume? I don't see any volume. Let's confirm here. So we'll start off with P1, V1, and T1, P2, V2, and T2, and see what happens. There they all are. So let's fill them in. So it's at 150 kilopascals and 35 degrees Celsius. So we've got 150 kilopascals, 35 degrees Celsius. Now here, if it's in Celsius, remember, we must change it to Kelvin, so we'll add 273. And 273 plus 30 gives us 303, plus 5 more gives us 308 Kelvin, right? Okay. And it says that the tank has a relief valve that opens at 250, so this will be P2, 250 kilopascals. We don't have any volume information, so we can take that right out. Up here we'll use the same, but cancel our volume. So we're left with P1 over T1 equals P2 over T2, like so. Okay, let's sub in some numbers. Our P1 is 150, our T1 is 308, our P2 is 250, and our T2 is what we're trying to find. We don't know what it is. So let's do our cross multiply. 150 T2 equals 308 times 250. Now let's get T2 all by itself, so we'll divide by 150 on both sides. And we get T2 equals what? So 308 times 250 divided by 150. I'm getting 513.3 repeating. Now, if we go back to our question, we have 2 digits here because that 0 is after the number but not after the decimal, so it does not count. 1 and 5 count, but not that 0. So we've got 2 digits here, 2 digits. Make sure you're not looking at this one, but you're looking at the original number that was given in the question. And same thing here, we've got 2 and 5 count, but not that 0. So we need 2 digits in our answer. So when we look at this answer, we'll keep the 5, we'll keep the 1, we'll cut it off here, and we're looking at the 3 to go up or down. Well, we'll go down. So T2 equals 5, 1. But we need to show that this is 510 rather than 51. So we need a 0 there just to hold our place and show where the decimal goes. So 510 is our answer, and our answer should need some units here. So it looks like Kelvin. Now, if we go back to the question, it says, at what Celsius temperature does the valve open? So we need to do a little calculation and figure that out. We'll take our 510 and we'll subtract 273, and we get 237, and this is degrees Celsius. So this will be our final answer. Okay, on to the last one. A 2.0 milliliter bubble of gas is released at the bottom of the ocean where the pressure is 610 kilopascals and the temperature is 5 degrees Celsius. What is the volume of the gas bubble when it reaches the surface at standard temperature and pressure? STP, it says. So remember, STP will be written on your test. Those values, you do not have to memorize them. They'll be written at the top of your test. let's go through and see what variables we were given here. Okay, so there's a 2.0 milliliter bubble, so that looks like a volume. There it is. And at a pressure of 610 kilopascals, right? Lots of pressure. And the temperature is 5 degrees Celsius. Okay, so we have all three variables in this question, so we're going to need to use the combined gas law. Our 5 degrees Celsius can't remain in Celsius. We need Kelvin, so we'll add our 273 to get 278 Kelvin. Let's look. It says, what is the volume? So we're looking at V2. What is the volume of the gas bubble when it reaches the surface at standard temperature and pressure? So standard temperature is 273 Kelvin. Standard pressure in kilopascals is 101.3 kilopascals. There it is. So let's write out our combined gas law. P1 V1 over T1 equals P2 V2 over T2. Our P1, we'll start subbing in some numbers. So P1 is 610, V1 is 2.0, our T1, 278. Our P2 is 101.3, V2 we don't know, and we'll put 273 on the bottom there. So let's do a little bit of a calculator work at this stage so that we can say 610 times 2 equals divided by 278. So we've got 4.3, now we want to keep lots of decimals, 4.388489. Because we're in the middle of the question, right? You don't want to round off to the end, keep a whole bunch of decimals. Now over here, our 101.3 divided by 273 gives us 0.3710622. V2. So we're going to divide both sides by that 0.3710622, and we'll do that on the other side as well. 0622. This cancels, and we're left with whatever that calculation is equal to V2. So let's go ahead and do it. 4.39 divided by 0.3710622. And I'm getting 11.8268. Okay. This volume is in milliliters. We want to make sure we have the right number of digits. If we go right back to our question, 5 degrees Celsius only has one digit, right? 2.0, that's got 2. 610, that's got a 6 and a 1, but that 0 doesn't count, so that's got 2 digits as well. 101.3 has 4 digits, and 273 was not even given to us in the question. That was our standard temperature. Actually, that's the same thing for P2 and T2. So when we look at all this, the lowest number of significant digits is this 5 degrees Celsius, so 1 significant digit. So we'll keep the 1 here in our answer. We'll be looking at this one to round up or down. Looks like we're rounding down. So we'll round down to 1. Keep that 0 in there to show that it's in the tens column rather than just plain old 1. We'll round down to 10. This is in milliliters. 10 milliliters equals V2. That's it. Hopefully you found this useful. Please go ahead and email me if you have any questions, and please pay extra attention to numbers 18 and 19 on those gases. Okay, I'll see you in class very soon.